You must be the person that Andrew told me about. Come on in, grab a seat. I've got your coffee here. Now, you're going to need it. So, Andrew told me that you're looking to learn Java, and apparently you've never done any programming before. It's cool. Don't worry. No, seriously, that's good because it means I don't have to sit here and spend the next hour undoing a bunch of bad habits that someone else taught you 6 years ago. You know. So I'm going to assume that you know absolutely nothing about Java, and that's exactly where I want to start. Forget about Spring Boot, forget about databases, forget about REST APIs, forget all about the stuff that people have been talking about with building with Java Online. So today we're just going to sit down and, you know, have a little talk about the language. So let's start with the obvious question. What is Java? So Java is a programming language, but more importantly, it is a way for us to give a computer some instructions so that you write your Java source code. That code becomes compiled into something that we call bytecode, and that bytecode then runs inside of this thing called the Java Virtual Machine, or you'll hear me refer to it as the JVM. Now, that's one of the really interesting things about Java, is that your program isn't necessarily compiled directly into instructions for one specific operating system. Instead, the JVM provides that environment for your program, and that's where you get the famous idea of write once, run anywhere. At least, that's the idea. So, Java's been around for decades, but the important part is that Java isn't stuck in the 90s. Modern Java looks very different from Java that your grandfather remembers, or I remember. So let's start with one of the simplest, smallest building blocks of the language. Imagine that you have this little container and say I tell you to put somebody's age in here. And that's basically what a variable is. It is a name that we give to some piece of information that our program needs to remember. So for example, int age 25. We're essentially saying, I want a variable that I'm going to call age so that I can refer to it later, and I want it to go into the memory containing the number 25. And we could also have things like string name Mike, or maybe is open true. Maybe we have a coffee shop. And already we're starting to teach the computer about the world that our program is going to be working with. A person's name, their age, whether or not something is open, how many coffees we have left in an inventory. That's programming. And you're taking information, giving it meaning, and giving your program a way to work with it as well. But now we need to make an important distinction because not all variables work in the same way. We have primitives versus objects. Java has primitive types such as int, double, boolean, char. These represent simple values. An int represents an integer. A boolean represents true or false. A char represents a single character. They are fundamental pieces of data. Then we have objects. For example, string name Mike. String is an object type, and this is where Java's memory model starts getting interesting because that variable isn't necessarily holding the entire object directly, it's actually holding a reference to an object. So think about it like this. If I give you a piece of paper with my address on it, that piece of paper isn't my host, it's just telling you where my host is. And that's roughly the idea of a reference. Your variable can point toward an object living somewhere else in memory, and that is where you'll hear programmers talk about the stack and the heap. Now, very simplified, the stack is associated with things like method calls and local variables, whereas the heap is where objects are allocated. So if I write int age 25, the int is a primitive value. But if I write person equals new person, now we've created an object. The person object lives inside of the heap, and the person keyword holds the reference to that object. Now, I want to be careful here because programmers sometimes explain this as primitives live in the stack and objects live in the heap. And that's useful beginner mental model, I suppose, but it's not the complete truth. So the JVM is free to optimize how things are represented. The important concept for you right now is that a primitive represents a value and an object variable represents a reference to an object. That's the distinction I want you to understand. And we'll get much deeper into memory later. But for now, let's make the program actually do something. So imagine we're building our little cafe application and we've got an integer of coffee count equals 10 and we want to know whether we still have coffee available. So we can use what's known as an if statement. So, if coffee count is greater than 0, print out that we still have coffee. Read that almost like English. If the coffee count is greater than 0, do something. We want to give the program an alternative path. If coffee is greater than 0, do this, else do this instead. And now your program can make a decision. That is a huge step because we're no longer just storing information, we're using information to control what the program does. And those conditions can get more interesting. So you can compare values and you can compare conditions with and or. Now, you can check whether something is equal or not equal. And eventually, you'll use modern Java features like a switch to make certain decisions a little bit cleaner. But there's one more thing that you need because making one decision isn't necessarily enough. And what if we had to do something again and again and again? For example, let's try out to see, you know, if let's say our cafe shop had 10 employees, and I don't want to have to write print out this name, print out this name, print out this name, print out this name, print out this name. That kind of gets ridiculous, especially if you become a big company and all of a sudden you have a few hundred. Like, whoa. So we can loop So for example, uh, if we were to look at this code here, we are telling Java, start with I at 0, keep going so long as I is less than 10, and after every iteration, increase that I by 1, and that's a loop. So you can also do things with a while loop when you don't necessarily know how many times that you have to do something. You just have to do it until a condition is false. And eventually, you'll even start using enhanced for loops when you're working with collections. So the important idea is conditions let your program make decisions, loops let your program repetitively work. So now we are starting to have the basic ingredients for an actual program. Uh, but we've still got a problem. We're putting everything into one big pile, and that's where classes come in. So let's say that we want to represent an employee. I could write something like this, and this class is the definition. It is the blueprint. It tells Java an employee has a name and an age. But the class itself isn't the employee yet. It is just a blueprint for how to create one. When we write something like this, even she knows, this is how we create an object. And this distinction is incredibly important because a class describes what something is, and an object is an actual instance of that class. So once you've understood that, object-oriented programming starts becoming much easier to reason about. And then we can add things like methods. How does this object do something? So maybe our employee isn't just storing information. Maybe they actually want to do something like make coffee. So this is where Java really starts to become powerful. We can model our application around things that exist inside of it. So employees, customers, orders, coffee, inventory, accounts, whatever our application needs. Now, I'm also going to introduce you into something that looks terrifying when you're new, and that is generics. Okay, so you may see things like list string, and you'll probably look at this and think, what the hell are those angle brackets? Less than, greater than? Um, don't worry, they're actually there to make your life easier. They are there to tell you that, okay, generics allow us to tell Java what kind of data is supposed to be inside of here. So this is a list of type string. The type is just the generic type. So this is also a list of integers, meaning this gives you type safety. So instead of throwing random objects into collections and hoping everything works out, we tell the compiler what belongs there, and eventually you will learn things like T or type extends number, and something extends this type. And then maybe you'll see something eventually along the lines of something is the super of some type. And yes, those do look ugly, but don't memorize them. Understand that the problem that they solve, that is the pattern that I want you to develop as you learn Java. Do not memorize syntax just because somebody told you to. Understand why it exists. And then that is where I want to jump ahead for a second. And because since we're learning modern Java, all modern and modern Java has some really interesting tools for concurrency. One of those things is called virtual threads. And traditionally, operating system threads have been relatively expensive resources. So if you wanted 1,000 of those tasks running concurrently, then you had to be very careful about how you manage those threads. Modern Java gives us virtual threads. So something like this, and Java can manage lightweight virtual threads for those given tasks. Now, I'm intentionally not going to do a deep dive into concurrency today because if I start going down that and scheduling, synchronization, race conditions, locks, structure, yada yada, we're going to be here till the cafe closes. All right, and that's not what this first meetup is all about. I want you to see where we're going because it isn't just some old language that developers mention in the history books that's been around forever. It's still evolving. And the Java that you're learning today is very different from the Java that I learned 20 years ago. Oh, there you are. Come on, grab a seat. I got your coffee. Here's where I'd like to introduce you into data structures and algorithms. Now, don't panic. I'm not going to be throwing a giant textbook at you. We're going to sit down the same way that I would teach a friend. Okay, we're just going to build something. Remember that cafe app thing that we were talking about previously? Well, yeah. Well, we got a problem. Go figure. So we've got inventory, um, and now we need a way to manage it. So we're tracking some different coffee beans. Okay, we've got espresso, Colombian, we've got decaf, French roast, we've got a little bit of Ethiopian, and tomorrow maybe we're gonna start having some tea, and maybe we're gonna have some few different flavors. Who knows? We'll eventually have thousands of coffee. Whoa, oh, yeah, okay. No, we're getting carried away. So the application just needs to answer a few things. Do we have this coffee? How many bags do we have? And what's the most recently added product? What's the cheapest product? What about products that are running low? Anything? And here's where programming becomes interesting because there are a lot of different ways that we could store information. And the way that we're going to choose to store it, we can completely change how quickly the program can work. This is what data structures are all about. So a data structure is simply a way to organize and sort data that we can work through efficiently. So think about our cafe for a second. If I dump every bag of coffee on the floor right now that we own, technically I still have all the coffee. But now finding the specific bag that I want, that's going to be a nightmare. All right. So instead, Maybe I organize them into shelves. And maybe I label those shelves and I organize them alphabetically. And then I create some sort of a coffee system where I can jump to the exact coffee that I'm looking for. Same information, just differently organized. And that is the core idea behind data structures. So we're not just asking, how do I store this? We're asking, how do I store this in an efficient way that I can use it later? Now, what exactly does efficiency mean? Um, this is where algorithmic analytics becomes into the conversation, or comes into the conversation, sorry. Uh, this is, you might imagine that we have 10 products, and I search through those 10 products, no big deal. Takes me no time. Now imagine we have 10, imagine we have 1,000 products, maybe 10,000, maybe 10 million. Suddenly, search seems to matter. And this is where you'll hear programmers talk about the big O notations. And you might see things like O1, O log of n, O of n, O of n log n, O of n squared. And when you're first learning things, that looks mathematical nonsense. It doesn't make any sense. It's just numbers and letters. But it's actually telling you and asking a pretty simple question. As the amount of data grows, how does the amount of work our algorithm needs to grow? That's it. O of 1? Let's start out with the easy one. O of 1, continuous time. So imagine I have a shelf with numbered positions, and I tell you to grab me the espresso beans. They're over on the position 7. Well, you don't care that the shelf has 10, maybe 100 different things in it. You just care about position 7. One operation, that's it. One simple thing. That is O of 1. Now, the amount of work does not grow with the size of the input. This is the reason that arrays are so fast. Now, what is an array? Well, an array gives us a block of memory where elements are stored sequentially. So something like espresso, Colombian, Ethiopian, decaf, because those elements are laid out in memory, Java can calculate where a particular index belongs. So a products array 3, we can jump directly to the location that we want, and that is O of 1, accessed by index. Pretty nice, but there's a catch. What happens when our cafe suddenly gets another product? Our array has a fixed size, and we need more room. We need a larger array. And that's where dynamic arrays come in. So Java has this thing called array list. And this gives us an array-backed structure that can grow. And when it runs out of capacity, it allocates a larger backing array, copies the existing elements, and then it just continues. So most of the time, adding an element to the end of is extremely efficient, but occasionally that resize operation can get expensive. And that is a really important lesson in DSA. As far as the fastest looking operation isn't always the whole story. You need to understand what happens underneath. For example, a linked list. So let's imagine that we don't want one big continuous block of memory. Instead, each inventory item could contain a reference to the next thing. So let's say espresso points to the Colombian, points to the Ethiopian, points to the decaf. A doubly linked set is basically the same thing, a step further, in that each element knows the previous one. So This can make certain insertions and removals very efficient when you already know the source node. But here's the trade-off. If I ask you to get me item 900 and a linked list can't jump instantly there. Instead, it has to walk through the nodes, which is an O of n. And suddenly, we have our first real lesson in algorithmic trade-offs. Different structures are good at different things. Now, let's forget inventory for a second. Imagine the cafe has a stack of orders, and the last order placed is the first one that we want to deal with. That's a stack. Last in, first out. So think of a stack of plates. You put one on top, you take from the top. You don't pull from the bottom unless you really want a mess. Now, imagine customers waiting for order, waiting for their coffee. First in, first served. That is a queue. First in, first out. And Java gives us abstractions for working with these concepts. For queues and double-ended operations, you'll often encounter the DEC, or double-ended queue. And you can add and remove from either end. Again, it's not about memorizing the API, it's about recognizing the problem. Do I need last in, first out? That's a stack. Do I need first in, first out? That's a queue. Do I need them both? That's DEC. Now, let's say your inventory grows to over 100,000 products, and somebody walks into the cafe and is like, yo, do you happen to have Ethiopian coffee? I don't want to start at the first product and then go to the second, the third, the fourth, and keep going until I find it. I want to be able to find it quickly. Now, this is where hashing becomes incredibly useful, and we can create a hash function. And the idea here is that we take some piece of information, maybe the product name, and then we turn it into a value that helps determine where the product should live. Now we can jump closer to where that product belongs, and this is the basic idea of a hash map. Now, this is good for the average case. Hash maps lookup are approximately O to 1, and that's pretty good, but there's no such thing as free performance. Two different keys can produce the same bucket. This is called a collision. And now our data structure needs a strategy for dealing with that. One approach is the separate chaining, others are open addressing, and as the table fills up, the load factor becomes important. Eventually, the table may need to resize and rehash its entries. And this is why understanding what happens underneath your collections matters. You don't have to have every implementation memorized and implement this every Tuesday morning. But you should understand the basic mechanics. And there is one more Java specific piece that you absolutely need to understand if you're creating objects to use as keys. You need to understand the contract between hash code and equals. If two objects are considered equal, they must produce the same hash code. Otherwise, your beautifully designed lookup system can behave in ways that will make you question every decision that you've ever made. Now, trees. Let's say you have your inventory and it's not exactly as flat as it used to be. Maybe we now have things organized in a hierarchy. So what was flat is now more like we have coffee, we have um, Robusta and Arabic. And underneath Arabic, we may have Ethiopian and Colombian. And now it's looking more like a tree. And a binary tree is a tree where each node has at most two children. Now, binary search tree or BST, gives us an ordering rule. So smaller values go in one direction, larger values go in the other. Now, that can make searching a lot faster and scanning a list. In a nicely balanced tree, you would wind up with something like O of log n. Um, and that's where things can get really interesting. So because what happens if our tree becomes horribly unbalanced? So instead of 50 at the point, we got 25, 75. We maybe we might end up with something like 10, 20, 30, 40. Yada 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 yada. Well, congratulations. Your tree has basically become a linked list. So we have these self-balanced trees, ALV trees, red-black trees, and they use different balancing strategies to keep these trees from becoming widely inefficient. And once you have trees, you also need to know how to walk through them. That's where tree traversal comes in order, pre-order, post-order, and breadth-first traversal. So each gives you a different way of visiting the nodes because breadth-first searching naturally works as a queue. And that is one of the coolest things about DSA. These concepts aren't isolated. They build on each other. Now, let's make a problem bigger. So the cafe doesn't exist in isolation. We have suppliers, we have employees, we have customers, delivery routes, locations, and maybe one supplier provides multiple products, and one of those products happen to come from multiple suppliers. Now, there's no longer no simple hierarchy. We're now into a graph. And a graph lets us represent relationships between things. For example, you have vertices and edges connecting them. And we might represent those relationships with an adjacency metrics or some sort of adjacency list. Um, then we can start asking real interesting questions like, can I get from here to there? What's the shortest route? What depends on what? And now we have some algorithms like depth first search, breadth first search, and Dykenstar's shortest path algorithm. I apologize if I pronounced that wrong. Um, and even topological sorting. So where we can order things based on their dependencies. For example, if we need to prepare something before another task can happen, a graph can help us model that relationship. Kayne's algorithm is one way of performing a topological sort. And now suddenly, we're not just sorting data anymore, we're solving problems. Now, but there's still one other problem. What if our inventory is a mess? We've got coffee, tea, sugar, milk, espresso, cookies, everything. And what if I wanted that to be sorted alphabetically? We need some sort of a sorting algorithm. And there are a lot of them out there. But I want you to understand a few important ones. Binary search can find an item in a sorted data with an O of log n. Merge sort gives us O of n log n behavior. A quick sort also gives us O of n log n, average case. And a heap sort uses a heap to achieve an O of n log n worst case performance. Now, there's a priority queue. Let's say I don't necessarily care what arrives first. I just care that it has the highest priority. Maybe we have coffee orders, regular coffees. Then an urgent catering order comes in, and another regular order coffee. The priority queue allows us to put the highest priority items in front of the other ones. Again, different problem, different structure, different solution. Big picture here. Well, I want you, and I know this sounds like a lot, and it is, but here's what I don't want you to do. Don't walk away from here trying to memorize hash maps are O of 1, binary search is O of log n, and merge set is O of n log n. That's not the point. I want you to start thinking differently. When somebody gives you a programmatic problem, don't immediately jump, what code do I write? Ask yourself instead, what information am I working with? How should I organize it? What operations do I need to perform? And how much data might I have? And of course, how expensive will these operations become if that data grows? So that is the mindset behind data structures and algorithms. You're learning to choose the right tool for the problem. Hey, hey, come on, grab your seat. I've got your coffee. All right. So today we've, we're going to get we've run into a problem. Um, Actually, it's the same problem every real application runs into. We've got data. We've just got nowhere to put it. So our our little cafe application. So we've got inventory, coffee, tea, milk, sugar. We have also got things like orders and customers, um, and last time we spoke, we spoke about different ways that we could organize this information in memory: arrays, lists, maps, trees, all sorts of fun structures. And that's all great until the application turns off. What happens to all of the data then? It's gone. I close the application, and tomorrow morning, Java starts with a blank slate. So it's not exactly going to work, and I don't want to count my coffee inventory every morning. I mean, we need persistence. Come on. We need somewhere that our data can live after the application shuts down. And that's where databases come into this. So, at its simplest, a database is a system for storing and retrieving information, and there are lots of different kinds of databases out there. But today, I want to talk to you about a relational database. And for our little cafe, we're going to be using something called SQLite. So this is nice because the database can live right alongside our application as a file. No database server, no configuration, no giant infrastructure, just here's our database. And now we can start designing it. So we can start out with our inventory. Um, we could create a table and call it products. And now, if you're completely new to SQL, then don't let this scare you. We're basically just shaping our data. We're saying that I want a table called products, and I want to have every product to have an ID, a name, a quantity, and a price. The table is our structure, and now each row represents one product. So our database might look something like this, and suddenly our Cafe has a memory. So there's something else important that we don't just want to store our data, we also want to make sure that our data makes sense. So if we look at name text not null, not null basically means that this is a required value. We don't want a product that doesn't have a name. And then something like quantity, integer, not null, default 0, well, that's saying that the quantity is an integer, it's required, and by default, we're going to set this to 0 unless otherwise specified. So these are constraints. And constraints are incredibly important because your application isn't the only thing that can make mistakes. If the database itself can enforce the rules, that's a whole other layer of protection. So now every product needs an identity. That's what our ID is. And it's our primary key. Primary key, well, this is a unique identifier in a row. So product 1, product 2, product 3, product 4. These IDs give us something stable to reference. And these are there are different ways that we can generate these IDs. We might use an auto increment, we might use a natural key, we may use things like a product code that already has meaning, or maybe we could use something like a UUID, and each approach does have its trade-offs. For our little SQLite application, an integer primary key is perfectly reasonable. So now imagine we have employees and orders and customers. Now, how do these tables know about each other? This is where relationships come in. And imagine an order, and an order belongs to a customer. Okay, so we have a customer. Customer 1 is Mike, 2 is Sarah, 3 is Andrew, and then we simply have an order of 101 belongs to customer 1, 102 to 2, 103 also belongs to 1. Now, that customer ID inside of the order is what's known as a foreign key. It is a primary key somewhere else that is being used internally as a unique identifier for what belongs with it. It is telling the database this order belongs to that customer. Now the database can enforce referral integrity. So if an order says it belongs to customer 42, but customer 42 doesn't exist, then that's a problem. And the database can stop us from creating that broken relationship. That is one of the beautiful things about a relational database. So they don't just store information, they can also enforce relationships between informations. And there are a few types of relationships that you're going to see constantly. There's a one-to-one, where one employee might have one employee profile. There is one-to-many, where one customer may have many orders. That's probably the relationship you'll see everywhere. And then there is a many-to-many. So imagine products and suppliers. So one supplier can provide multiple products, and one product could potentially come from multiple suppliers. Now, you can't just stick one supplier ID onto the product and call it done. Instead, we introduce another table, something like this, where product ID of 1 belongs to supplier 10, product 1 to supplier 11, product 2 to supplier 10, and the little table is called a junction table or a join table. And now we've represented a many-to-many relationship. So what happens if I delete a customer? What happens if I delete their orders? We need some rules. And maybe the database should delete the related records too. That would be on delete cascade. Now, maybe we want to keep the related record but remove the association. So that where we do on delete set null. And this can make sense. These decisions are part of the database design, and they matter because deleting a row isn't as simple as just delete it. Your data may belong or be connected to other tables. You don't know. So now you've got your database and you've actually got it, you've now need to talk to it. This is where SQL, or structured query language, comes in. And SQL is a declarative language, and that is an important distinction. With Java, you tend to tell the compiler how to perform a task. With SQL, you genuinely tell the database what data you want. For example, select all from products. This basically, give me everything in the products. Now we can filter it, select all from products where quantity is less than 10, and we're basically saying, give me all the products that we're running low on. And we can then sort it, give me select all from products ordered by price descending. And this gives me a list of products from most expensive to least expensive. Maybe we can limit this. Select all products, limit 10. And we can also give it an offset if we want to start maybe with product 5 and get the next 10. This is the foundations of pagination. Now, what if I don't want individual products? What if I want information about the products? What if the product, how many products do we have? What is our average price? What is the most expensive thing? What is the total quantity of our inventory? These are where aggregate functions come in. Things like count, sum, average, min, max. For example, select the count of everything from products. And this basically says, how many products do we have? We can then group this information together as well. So imagine we have an inventory with categorized types, coffee, tea, pastries. So we could use something like group by and aggregate those categories. And then having lets us filter the grouped results. And this is where SQL starts to become incredibly powerful because we're not just retrieving rows anymore. We're asking questions about our data and getting answers. So now we're going to do something that initially looks a little weird, but let's say I want to know which customer placed this order. The customer is in one table and the order is in another table. So we join them. Select customers.name, orders.name.id from customers, inner join these orders on the customer ID is equal to the orders.customer ID. And okay, read that almost like this, okay? Give me the customer's name and the order ID where the customer is connected to that order. And that's an inner join. But there are also different kinds of join. A left join lets us keep everything from the left table even if there isn't any matching rows on the right. There's also a right join, a full outer join, and even a cross join. So a cross join, okay, that a cross join produces a Cartesian product. So meaning every row from one side gets paired with that of the other. So usually that's not what you want. But understanding that understanding what it does is important. And the point isn't to memorize a list of joins. The point is to understand that our relational data is split across tables, and that SQL gives us ways to bring those pieces back together the way we want them. Now, I'm going to show you something a little more advanced. Suppose I want to number products within each category. I would do something like this. And that's a window function. And partition by lets us perform calculations across groups of rows without collapsing those rows into a single result like group by does. And you don't need to master this today. I just want you to know that SQL can do some remarkably sophisticated data processing. And that's why knowing SQL is so incredibly valuable. Um, Even when you're working with a framework that tries to abstract all of that away from you. But we'll get into Spring Boot later. Now, let's talk about something that might save us a little bit of save us from creating a terrible database. Imagine I store this, okay? Order ID, customer name, customer email, product name, and product price. Looks fine at first, but what happens when the same customer places 20 orders? Then I'm storing their name and email 20 different times, and that's when their email, what if their email changes? It's no longer going to sync up. Now we've got 20 different records that we need to update, and that is data integrity. It's a problem. So normalization is about organizing relational data so that we reduce the unnecessary duplication and dependency problems. So you'll hear terms like first normal field, second normal form, third normal form, and eventually you'll get into a voice cod normal form. And I'm not going to make you memorize a bunch of textbook definitions. That's not what this is about. The important thing is to search for the piece of information at the place where it logically belongs. Customers belong in a customer table. Products, a product table. Orders, an order table. And relationships connect them together. So we're trying to avoid turning our database into a giant spreadsheet where everything just gets duplicated everywhere. Um, so there's another problem. Our database works beautifully with 10 products, but then once we start to get to that 10 million range, we run into, select all from products where name is Ethiopian, and suddenly our database has a lot of rows to look through. So we can create this thing called an index. And think about the index at the back of a book. If you want to find something, you don't read the entire book. No, you flip to the last, look at the index, and go from there. Databases use data structures such as B trees to build indexes that can make lookups dramatically more efficient. Um, so we could create an index on products.name, or perhaps a composite index involving multiple columns, and something we can design. Um, Sometimes we can design a covering index so the database can satisfy a query directly from the index without needing to fetch the actual full table row. But indexes aren't exactly free. Nothing is free. They all take space. So every time we insert or update data, the index also needs to be maintained. So you can you don't just throw an index on every column and call it a day. Uh, you instead design indices around queries that your application actually performs. So now here's something I want you to get a little bit comfortable with. Don't guess, measure. If your query is slow, we can ask the database how it plans to execute this code. So with SQLite, we can use explain query plan, and in other relational databases provide similar things with things like explain analyze. Um, and these tools let us investigate what is actually happening in the database. Is the database scanning the entire table? Is it using an index? Is the query doing something unexpectedly expensive? Because just writing select whatever is easy, but writing SQL that performs well against millions of rows and large amounts of data, that is a different skill. Now, let's imagine something happens at our cafe. Okay, a customer buys 3 bags of coffee. We need to create an order, add the ordered items. We need to reduce the inventory. And what happens if, you know, step 1 succeeds, 2 succeeds, and then 3 fails? We fail to update. Now we've got an order saying that the customer bought coffee, but our inventory still says that we have it, and our database is inconsistent. This is where transactionals come into play, and a transaction lets us treat a group of database operations as one logical unit. So everything either succeeds or we roll everything back. And that brings us to something else that you're going to hear a lot in the database development, ACID. So atomically, the transaction happens as a unit. Everything succeeds or else it fails. Consistency. The database moves from one valid state to another valid state. Isolation. Con concurrent transactions shouldn't interfere with each other in ways that produce invalid results. And then there's durability. Once a transaction has successfully committed, the database should persist the results. And these 4 properties are the fundamentals of reliable transaction systems. And but isolation gets particularly interesting because multiple things can happen at the same time. So imagine 2 people are trying to work with the same inventory. One transaction is changing our coffee quantity while another transaction is reading it. And while what exactly should the second transaction be allowed to do and see, that's where transaction isolation levels start to come in. So you'll encounter levels such as read uncommitted, read committed, uh, replicated read, and serialized. And these levels determine how much one transaction is isolated from another. Without getting too deep into the weeds, um, they exist to deal with problems such as dirty reads and seeing data that another transaction hasn't committed yet. Non-replicated reads are readings that the same row. Sorry, it's when you're reading the same row twice and getting different results because another transaction changed it. And phantom reads, these are where a query returns a different set of rows because another transaction inserted or removed matching records. And this is where database programming starts to become less about can I store this and more about Can I keep this data correct when hundreds of thousands of things are happening at once? Hey, there you are. Come on in. Have a seat. Have a seat. I got your coffee right here. So, we've got another problem. Our cafe needs customers. So, I'm not just sitting here staring at a database. We need real customers. Um, they need to be able to open the website, see the coffee and food, place an order, and have it delivered. So, um, our little cafe application is going to be turned into a web application. And this is where I want to introduce you to something that you've probably heard about, Spring Boot. Now, why do we need Spring, you might ask? So, it's a good question, because before I show you a single annotation, I want you to think about what it is that we've already built. We've got classes, we've got an inventory, we've got database, and we've got business logic. Now we're going to add a web layer to that. So imagine we have our customer come into our web controller, go into our order service, down to our product repository, which is our SQL database. And the customer makes a request, the controller receives it, the service layer decides what needs to happen, and the repository talks to the database. Simple enough. Here's the problem. Who creates all those objects? Who creates the controllers, the service, the repository? And how does the controller get all of the services that it needs? You could do it all yourself, and technically there's nothing wrong with that. But now imagine 50 classes, 100 classes, 500 classes. Suddenly, your application is spreading. And a lot of the time, worrying about how to construct itself. And that's where Spring comes in. So, Spring introduces a concept called inversion of control, or IOC. And it sounds much easier or much scarier, sorry, than it actually is. Normally, your code controls object creation. You would say new product service, provide the required arguments, and you create the object. With Spring, you hand that responsibility off to the framework itself. We are basically saying, um, Spring, you manage the objects for me. And Spring's application context becomes the container responsible for managing those objects. Those managed objects are called beans. And that's the word that you're going to hear constantly. Bean. Don't overthink it. A bean is essentially an object that Spring manages inside of its container. How does Spring know what to do? Well, we can simply tell it. So for example, if we had a product service, we could slap on at component. And Spring sees the component during an application startup and registers it as a bean. Now there's a few others that we can do that are a little bit more specialized. You might see things like at service for business logic, at repository for persistence related components, or even at controller for web-based controllers. Now, these are all ways of communicating intent. We're basically saying, Spring, this class is a part of my application. Please manage it for me. And there's also other ways that you can do this. We can be explicit by creating a bean ourselves. We can do so by saying something like product service, return new product service, and we tag it as a bean. Now, this gives us more explicit control over how that object gets constructed, but we still got a problem. Remember our controller? It needs a service, the service needs a repository, and the repository needs access to the database. That is a chain of dependencies. And instead of the controller doing all of this manually by doing service equals new product service, we can simply say that the product controller private final product service and contract that in our constructor. And then Spring sees that constructor and it says, oh, there's a controller that needs a product service. I've got one of those here that I'm managing. Let me throw that into here. And that is what we call dependency injection. The dependency is simply supplied to the object instead of the object creating the dependency itself. And that is an incredible, important distinction. You may see people write something like product service with a little auto wired annotation there. That is field injection. And you'll see this in plenty of tutorials, and I don't want you learning it as default. I'd rather you use constructor injection because now the object tells us exactly what it needs to exist. And if a product controller requires a product service, you can't really construct one without the other. And that is good design. The dependency is explicit and it is immutable if we make it final. And this is much easier to test because we can simply provide the dependency ourselves. For example, some sort of fake product service, and no Spring required. That's one of the big advantages of dependency injection. It reduces coupling. Now, let's say our cafe eventually has two payment processors. We're handling cash, and now we're introducing credit card. So both of these implement payment service, and Spring now has a problem because you can ask it to give me a payment service, and it's going to turn around and say, huh, which one, bro? So this is where we have things like at primary, where we can tell it this is the primary source, and otherwise we can say at qualifier, and we can, tell it that this lets us explicitly identify which bean that we want. So we can use primary to tell Spring which implementation should be preferred, and qualifier lets us explicitly identify other beans that we want. So again, the important part is not memorizing the annotations, it is understanding the problem. I've got multiple objects that need satisfying with the same dependency. Which one should I inject? So now let's zoom out a little bit, um, because we're talking about Spring creating objects, but what's actually happening? Um, when the application starts, Spring creates an application context, and that context becomes the environment where our beans are registered and managed. It discovers components, it produces configuration, or it processes configuration, it figures out dependencies, it creates the objects that it needs, and it wires them all together. So instead of our application looking a little bit like controller has new this, new this, new this, we come out with something that looks a little bit more like this. And Spring is managing the object graph for us, and that's really what the IOC and DI are actually buying us. Now, here's something people often skip when they're learning Spring. The objects don't just magically appear. No, beans have a life cycle. Spring starts building the application context. It discovers the beans definitions. It creates and wires the dependencies, and then it applies various post-processing steps. And eventually, your application is ready to receive requests. Now, you can hook into this life cycle. For example, inside of an entity, you can use post construct, or inside of a bean, post construct, um, which allows you to do some sort of initialization work after it's been constructed. You can think about this as having like a class initializer after it's been constructed versus a constructor. And then you can have something that is going to happen when the bean is destroyed. So pre-destroy. Um, this just is some cleanup work. And these are also being They're bean post processors that allow Spring infrastructure to inspect and modify beans during their life cycle. And that is one of those places where Spring starts revealing just how much um, machinery is underneath those simple annotations. The bean's scopes are not every bean has, okay, so not every bean behaves the same. Okay, so by default, Spring beans are genuinely singleton scoped, meaning that Spring Manager um, Spring manages one shared instance of that bean within the application context. There's also prototype. This is where Spring creates a new instance every time that it's requested. And in web applications, you can also have a few other scopes tied to a request or session. So you have singleton, prototype, request, and session. These aren't just vocabulary words. They're telling Spring how long should this particular object live. And again, we're starting to see a bit of a pattern. Spring isn't really creating objects. It's managing the life cycle of our application's object graph. Now, let's say your cafe needs to run under different configurations. Um, so maybe we have a cafe name, a delivery radius, a maximum order size, a database location, and we don't want to hard code that stuff into our classes. Instead, we want to put these inside of a configuration, such as an application.properties or application.yaml. For example, we may have something like cafe.name equals midnight cafe. We may have something like cafe.delivery hyphen radius is equal to 15. And Spring Boot can then make use of these available options through values. And you may see at value, and then inside the parentheses, you'll see a reference to the name in the application. So cafe.name. But when you have a group of related configurations, such as the name, display radius, yada, 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 um, because instead of sprinkling individual configurations throughout your application, you can actually bind these to a single property within a Java object. Okay, so let's say we have cafe properties. It's Java record, and it contains a name and a delivery radius. Notice how the hyphen spaced words are now camel cased like Java. Just notice that. Okay, so we can tell this at configuration properties that it's going to have a prefix of cafe inside of the application.properties. And anything that persists cafe with the variable names, cafe.name, cafe.delivery hyphen radius, now configuration becomes something that our Java code can easily reason about as a type, which is much nicer. Now, here's another problem. What about when we have more developers um, or more development stages? So we don't necessarily want our development environment configuration to slip into production, much like we don't want our test one to slip into production. Maybe our development uses some sort of local SQLite database, while production uses a hosted PostgreSQL, and maybe development enables extra logging that production doesn't, and this is where profiles can come in. So we can have a dev profile and a prod profile, and we tell Spring only use the configuration when the dev profile is active. So then we would simply annotate, and you're going to notice that annotations are a thing with Spring. You can conditionally register beans with at profile. So that at bean we made earlier, yeah, we can slap a profile on that and run this bean on this profile. Now your application can behave differently depending on the environment that it's running in. Same application, just different environments. Now, we've also reached the part where beginners usually say, okay, but Spring Boot is magic. And I understand why they feel like that. But you add a dependency, you write Spring Boot application on the first main class, and you run the application. And suddenly, you've got a web server. You didn't even create the server. You didn't manually configure every component, but something happened. This is Spring Boot's auto configuration. Spring Boot looks at what's available in your application's class path and configurations, and it then tries to configure sensible defaults for you. For example, if you add the appropriate web dependencies, Spring Boot will configure an infrastructures needed for web applications. And this can all be started from that annotation on the main class at Spring Boot application. Now, which also includes the auto configuration uh, mechanics. However, there is one more thing. I don't want you to think Spring Boot just knows what I'm doing. It doesn't. It follows a predefined set of rules. Spring Boot's auto configuration is heavily based around conditions. So you may see things like conditional on class, meaning only configure this if a particular class is involved. Or maybe you'll see conditional on missing bean, which is just saying if the developer hasn't provided their own version, I'm going to provide my own. Maybe you might see conditional on property, which means only enable this configuration if a particular property says we should. And this is the part that makes Spring Boot feel intelligent, and it's really a collection of carefully designed conditions. And that's why adding a dependency can suddenly cause Spring Boot to configure a whole bunch of infrastructure and feel like magic. So here's a little trick that I want you to remember. If Spring Boot is doing something and you're thinking, where the hell did that configuration come from? Don't guess. Start the application with debug information enabled. Spring Boot can provide you a con it can provide a conditions report. So it's going to show you which auto configurations matched and which ones didn't. And then suddenly magic becomes mechanical work. And once you understand the mechanisms behind it, Spring Boot becomes a lot less intimidating. So let's put all of this together, and our customer opens up the website. They see Midnight Cafe. They see options for tea, coffee, pastries, breakfast, lunch, and they go through and choose a few different items, and they put them in their order. And the request comes through into our web controller. The controller depends on the order service. The order service depends on the product and order repositories. And those repositories talk to our database. Meanwhile, Spring manages the relationships between all of these components. And that's the first time our little cafe project starts looking like an actual application. Hey, come on in, come on. Here, I got your coffee. Um, 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 we have a problem. I built an API, and it works. Customers can browse the menu, they can place orders, and they can check out their orders. They can check their orders. Everything looks great until I discovered an issue. So one customer can look up the order of another customer. Yeah, that's bad. Real bad. So today, we're going to fix it. And while we're doing so, I'm going to show you what starts to happen when our a little Spring Boot application stops behaving or stops being a little demo and starts looking more like production software. And our customer needs to interact with the cafe somehow. So we expose some endpoints. Looks a little bit like this. Um, this allows us to um, we created a REST controller. Um, and so we have each of these endpoints for orders, for products, and so now Spring knows this class handles this request. Um, and then we went and mapped individual operations with get mappings and post mappings, and we were responding with response entities. But the URL gives us the order ID. The path variable gives us the ID to our Java method, and we create the order. Spring takes the incoming request body and turns it into the Java object for us. That's pretty convenient. But there's a problem. We're trusting the client. We shouldn't. Bad practice. Never trust the request. Imagine a customer sends us a payload that looks a little bit like this. It doesn't really make sense. Or maybe they send us this. Or maybe this. And we need to validate the input before it gets anywhere near our business logic. And that's where a Jakarta bean validation comes in. So we can do things like this to our request. We can add an not blank, an email, and a size with some minimum and maximum restraints. We can also override the default messages. And then we can tell Spring to validate the request body. And now invalid input can be rejected before we even process it. And that is an important distinction. Validation isn't business logic. Validation answers, is this request structurally valid? And the service layer can then answer the question, does this request make sense for our business? And for example, a quantity of -5 is invalid input, but asking for 500 coffees when we only have 20 in stock is more of a business rule. Different problem, different layer. And now let's suppose the customer is asking us for an order number that doesn't actually exist. What should our API do? We don't want any of our controllers writing their own error handling, okay? So we do not want to see try catches inside of our controllers anywhere. That is ugly very quickly. So instead, we want to utilize centralized exception handling. So Spring gives us this thing called REST controller advice that we can use, or exception handler, so that we can create our own classes for handling exceptions. And we can place the responsibility for turning these exceptions into consistent HTTP responses. And modern Spring applications use this problem detail response based off of the RFC 7807 instead of returning something random like error, something went wrong. We can return something more structured, such as type of error, the title, object, order not found, status 404. Detail, the requested order doesn't exist. And now our API has a consistent language for failures. And that's important because production applications don't just need successful responses, they need predictable failures. So our API needs to actually save orders. And we're going back to the database. This time, instead of writing all of our SQL manually, we are instead going to introduce Spring Data JPA. So we can now define our order with an entity tag or entity annotation and a table annotation. And something that I would like to point out here is that both the entity and the table take a name. The table name is the name of the table that will show up in our database, whereas the entity name is how we reference that table inside of a SQL or SQL query. Now, we also add in our ID, generated value, and Spring Data can map the Java object to our relation database. And we can model relationships as well. An order might belong to one customer. So many orders, one customer, that is a many-to-one relationship. And maybe a customer, they might have many orders. So we might have one customer with a list of orders that is a one-to-many mapping. And this is where everything that we learned about relational database starts connecting to Java. And the database has relationships. Our Java model represents those relationships. JPA gives us a bridge between the two. Now we need to actually retrieve these orders. So we create an order repository that extends a JPA repository, taking in an order as the key and a long as the value. And suddenly, we now get operations such as save, find by ID, find all, and delete, to which we can also define query methods, for example, find by customer ID, and provide in the long value of the customer ID. And then Spring will actually derive the query from the method name. And, you know, when things get a little bit more complicated, we can override it and write our own JPQL with at query, providing in the SQL syntax or statement generally defined by the database specific behavior. And when our cafe eventually has thousands of orders, we don't really want to return every order in one big response. So we want to introduce something called pagination. Pagination is something that you can ask for a specific page, like in a book, give me page 3, which has 20 orders. And you will get essentially offset, 20 times 20 times 20 to the third spot, and you'll get the next 20 indexes. And that's how pagination works, basically. But things can also get a little dangerous. Now, remember our security problem? The customer asked for order 42, and our controller is like, cool, I'll get you 42. And it responds with exactly that. Seems fine. Except, what if order 2 belonged to Andrew and, I'm Mike? Our API just handed me somebody else's order. The database did exactly what we asked of it. The repository did exactly what we asked of it. The controller did exactly what we asked of it. The problem is that nobody has asked the question of whether or not I was allowed to see it. And that is where authorization uh, is the problem. So let's get this out of the way. The distinction is incredibly important. Authentication asks, who are you? Authorization asks, are you allowed to see this? So those are not the same thing. Spring Security helps us handle both, and we can configure a security filter chain to define how HTTP requests are secured. So maybe API/products is public. Anyone can go there and see what products we have. However, API orders/anything is going to require authentication because now the customer has to prove who they are so that we can get what they want. But we're still not exactly finished because knowing who someone is doesn't automatically mean they're allowed to access every resource. So imagine I'm logging in as customer number 15 and I request order number 42. Spring knows who I am, but our application still needs to determine, does order 42 belong with customer 15? That is authorization. And that is where our business logic needs to be involved. So we might enforce ownership in a service layer, and we can also use method level annotations such as pre-authorized, where we can extract security expressions. Um, and the exact security expression depends on the application. So the principle is more or less even more important. Never trust the ID coming from the client as proof of ownership. Just because I can change order number 42 to order number 43 doesn't mean I should suddenly gain access to order number 43. And it's exactly the kind of thing that you need to think about when building APIs. So we'll start out with something like passwords. And if we're authenticating customers, we obviously need some kind of a password. But never store passwords in plain text in our database, ever. Passwords need to be hashed using some kind of secure, trusted, proven hashing algorithm. Don't go writing your own. In Spring Security, we can make use of something as simple as bcrypt password encoder or Argon 2, which needs a little bit more customization to do so. But to keep it simple, bcrypt password encoder. The important concept is we don't need to know the customer's original password later, okay? We only need to verify that the password they provided matches the stored hash that they originally gave us. So security isn't something that we just bolt on at the very end, okay? We need to take it in from the very beginning. So let's place our order. Our customer orders 2 espressos and a croissant. We need to create the order, add the order items, reduce the inventory, and maybe record the payment, and that is multiple database operations. What happens if the first few succeed and then maybe the fourth one fails? We don't want half an order sitting in our database. This is where @transactional comes in. And we can define a transaction boundary around the operation. either the entire operation succeeds or it all rolls back. And when we're performing read-only operations, then we can sometimes communicate that intent with a read-only equals true added onto into the parentheses. So again, these aren't just annotations to memorize. We are expressing a boundary around a business operation. Now, our API works, but production has a funny way of exposing problems. Suppose we have 50 orders, and each order has a customer, and our application then retrieves the 50 orders, and then it starts querying the database again and again to retrieve every order's customer's information. The query, then 50 more. Congratulations, you've just discovered the n+1 query problem. Achievement unlocked. So your API might work perfectly the first 5 orders. Then someday somebody imports 50,000 orders and suddenly your database is screaming at you. There are strategies for dealing with this: join fetch, at entity graph, projections, and carefully designed queries. The lesson here is that ORMs make database access easier. They don't make database performance irrelevant. You still need to understand what SQL is underneath. Now, let's say this happens in production. The customer starts saying, your website's a little slow. What do? Sit in a server room and stare at the computer. No, we need observability. So Spring Boot has this thing called Actuator, and this gives us an operational endpoint such as actuator/health and actuator/metrics. So when we can use these health informations to understand whether the application is healthy, and we can use the metrics can help to understand things like request counts and performance. So now we can create custom health indicator beans, and eventually we can export metrics to something like Prometheus and start monitoring the application properly, because production software needs to tell us what's happening. And also, here's a part that might be the least exciting in the world, but it's probably one of the most important: testing. Because how do we know that our security fix actually works? We have to test it. We don't just write the code and hope that nobody discovers it. So we would write a unit test with JUnit, something like this. And Macchiato can let us isolate dependencies. We can mock a repository, mock a service, provide controller inputs, and test one piece of business logic at a time. That's unit testing. But sometimes we need to test the actual Spring layer itself, like the web layer. And we can do that with this thing called @webmvc_test. You can test our controllers and HTTP behavior without loading the entire application. Then Spring Boot test, it can give us a much broader integration test. And for repositories, we have something like @Data JPA test. Lets us focus specifically on the persistence layer. Different tests answer different questions. But now, here's something that I would like you to be careful about. If your production uses PostgreSQL, don't assume an in-memory test database behaves like a PostgreSQL database. Your tests might pass, but your production might still break. And that is why tools like test containers are so useful. And we can start an actual database engine inside of a container for our integration tests, and our tests can then talk to something much closer to the database that we're actually going to deploy against. And now we're testing more than just, does my Java code compile? We're testing, does my application actually work against infrastructures that it is designed to use? So it's much better to test. Now, let's go back to the original problem. One customer was able to access another customer's order. That sounds like a big bug, but let's look at what we had to think about. We needed REST endpoints, request validation, centralized exceptions. We needed database persistence, transactions, authentication, authorization, password hashing, testing, observability, and performance. And that's what happens when software becomes real. You stop asking, does the code work? And you start asking, does the system behave correctly when real people use it? So think about the architecture that we've just built. And surrounding all of it are validation, exception handling, transactions, testing, metrics, and security. This is the difference between writing a Java program and engineering a system. Hey, you made it. Great. Come on in. Come on in. Um, so, you know, I was thinking about where we started the first time that we sat down together, and you didn't know a single thing about Java. But then we talked about variables, classes, loops, memory, and we kept meeting data structures, algorithms, databases, SQL, Spring Boot. Um, and now, I mean, we've actually built something. We've got a small little cafe application. Customers can browse our products. They can place an order, and our application can store that information. We've got an API. We've got authentication, authorization, tests, and monitoring. And we've only got one problem left. We have to put this thing on the internet. Now, running our application on our laptop is easy. We run a command or we hit the button in IntelliJ. There it is. Everything works. But now, production. Production doesn't care about your laptop, okay? Production has real customers, multiple users, unreliable networks, servers that can fail, large files, and concurrent requests. And suddenly, our little application needs to grow up. So let's talk about what can happen next. Imagine that I've just placed an order and I don't want to sit here and refresh my page every 5 seconds. Is my coffee ready yet? Is it ready yet? Is it ready yet? That annoying kid in the back seat. Are we there yet? Are we there yet? Are we there yet? No. So that's terrible. That's a terrible user experience. Instead, I want the application to tell me order number, whatever, order received, or preparing your order, it's out for delivery. And when the status change, I want the customer to see it immediately. And that is where WebSockets come into the picture. So, unlike traditional request response models, where the browser asks the server for something and whatnot, WebSockets actually allow us to establish a persistent bidirectional connection so that the client and server can communicate with each other in real time. And in Spring, we can build this using Spring WebSocket. And for messaging applications, you'll often see Stomp layered on top. Um, Instead of constantly asking, is there anything new? The client can maintain a connection and the server can simply push an event when something happens. And that is a completely different style of communication. And suddenly the cafe feels alive. But there's something that we need to think about. Okay? So remember when we fixed that problem where the customer could access other customers' orders? Well, we can't just forget about security now that we have WebSockets. Uh, there's another challenge. Our application needs to work across multiple requests. So maybe the customer logs in on their phone next and they make an order and then another one. And we need to know who they are. One common solution for this is a JSON web token or a JWT, JOT. The idea is that after authentication, the server assigns a token. The client then presents said token to any subsequent request, something conceptually like login, password, username, authentication, JWT is generated, sent to the client, comes back as a bearer token in every other request, and Spring just handles it. So the token contains claims about the actual user, and it is a cryptographically signed so that the server can verify that it hasn't been tampered with. You may see things like HMAC based signing or even asymmetric cryptographics such as RSA. And the important part is the server verifies the token before trusting the claim. So earlier we talked about Spring Security and a filter chain. So now we're going one level deeper and we're going to add a run before. And we are going to add in this new filter, which is going to be something like a once per request filter. And this is going to look for a bearer, an authorization header with the bearer token. It's going to extract the JWT, validate it, and establish the authenticated security context for that request. And once again, all of the concepts that we've learned are starting to stack together. You've already understood HTTP, you understand objects, Spring dependency injection, security, and now we're just combining them. So that's the whole point of this roadmap, is that everything just comes together. So now let's say our cafe expands. Maybe customers can upload a profile picture. Maybe we're allowing catering customers to upload their event menu, and maybe employees need to upload receipts. So suddenly we're dealing with files, and Spring gives us a multi-part file for handling multi-part uploads. And um, this is where production thinking comes in. You don't necessarily want to load a massive file completely into memory. Imagine somebody uploads a 2 GB file. Please don't put the entire thing into a byte array, whatever you do. Instead, we need to start thinking about streaming it. So we can stream the incoming resource into storage. And maybe that's a local file system, or once we're running things in the cloud, maybe we're looking at something like Amazon S3, whatever. And we need to think about buffering and size thresholds, because once again, a solution that works perfectly for a 500 kilobyte file can become a disaster when somebody uploads something much larger. So where are we going to run this at? Okay. Where does our application actually live? Well, right now it's on my computer. Well, that's not production. We need to package the application. And this is where Docker comes into hand, because Docker is incredibly useful We can just build a Docker file, our application gets built, and then we put the resulting application into a container image. But we don't necessarily need to put the entire development environment into that production. So we do things in a multi-stage build, where the first stage builds the application, another stage contains only what we actually need to run it, and we can use a minimalistic Java runtime image. The result? A very small container with less unnecessary software. A cleaner production artifact, and now our application becomes something that we can consistently deploy and scale. But remember our database? Yeah, well, production needs that too. So um, our application might eventually benefit from caching. So we may want to add in Redis to this as well. But we don't want to manually configure all of this every time we start our development environment. This is where Docker Compose becomes useful. We can describe our services, our application, our database, and our Redis cache. And then the network between them is taken care of by the compose. So all we have to then run is Docker compose up, and our development environment comes alive, which is a huge improvement over everybody download Postgres, install this exact version, configure this port, install Redis with this. Containerization lets us start describing our environment as infrastructure. Now, why did I sneak Redis into the architecture? Because sometimes we don't need to ask the database for the same question over and over and over. So imagine our cafe menu. 1,000 customers hit the endpoint for API products, and the menu doesn't change every time. So instead of hitting the database for every single request, we could cache or store the frequently used accessed data or frequently accessed data, which is where something like Redis can help. But here's another lesson. Don't add technology just because it's popular. Okay? Caching introduces complexity. You need to think about invalidation, expiration, consistency, memory usage. So if PostgreSQL already answers the query quick enough, maybe you don't need a Redis cache. The best architecture isn't the one with the most amount of technologies crammed into it. Sometimes it's the one that solves the actual problem. At this point, our API is getting pretty big. We've got an API for products, orders, customers, authentication, files, delivery, and if another developer jumps on the project, how do they know what all of these endpoints do? How do they know what all of the, what a request should look like from each of these? What does the response contain? What errors can happen? What we need some kind of a documentation, and it can't just be a Word document in the cloud that gets outdated every day. That we can just generate an open API specification. So tools like Spring Doc Open API can integrate with Spring and generate API documentation for our application. Now, developers can open up the interactive API page and see the available endpoints, understand the requests that the response models, and they can experiment with the API. Our API isn't just code anymore, It is a contract. So now here's something that I really want you to understand. When you're learning to program, you spend a lot of time thinking, how do I make this work? That's normal. That's how you learn. But eventually, you will start asking different questions. How does this behave when 10,000 users use it? What happens when the database goes down or somebody uploads a massive file? Maybe two users modify the same thing at the same time. Maybe the network disappears halfway through a request. Someone tries to access data they shouldn't. Maybe we deploy the new version, or maybe one service just happens to go offline. These are software engineering at its finest. You're no longer just writing code, you're designing a system. And here's some advice that I would give myself if I were talking to myself 20 years ago. Don't look at this and think, I need to learn all of this before I can get a job. No, 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 no. You don't. You're going to forget things. You're going to get stuck. You are going to open documentation pages and think, what the hell am I looking at? That is normal. I've been doing this for a very long time and I still look things up. The difference isn't that experienced developers remember everything. The difference is that they've built enough foundations to understand what problem they're trying to solve. And you don't need to memorize every Spring annotation. You just need to understand dependency injection. You don't need to memorize every single, algorithm. You just need to understand how to choose the right approach. You don't need to memorize every SQL statement. You just need to understand relational databases. You don't need to know every Docker command. You just have to understand that you're trying to package and deploy. So that's probably the most important thing that I can tell you. This roadmap is not a finish line, it's a foundation. From here, you can go deeper into Spring security, learning things like OAuth 2 and OpenID Connect. You can explore distributed systems, learn Kubernetes, study cloud platforms, go deeper into PostgreSQL, and learn messaging systems like Kafka or RabbitMQ. Explore observability, learn system design, and study performance engineering. Maybe you specialize in backend development. Maybe you move towards platform engineering, maybe cloud architecture, maybe DevOps. Maybe you discover that you absolutely love databases for some weird reason. And maybe you decide that you hate all of it and just become a game developer. That's all cool. The point is, now you have somewhere to start. So if you're serious about becoming a developer, don't spend your entire career chasing frameworks. Frameworks change, libraries change, cloud providers change, even languages change. The fundamentals stick around. Learn how computers work. Learn how data is represented, how algorithms work, databases, networking, HTTP, security, testing. Learn how systems fail. And most importantly, just build things. Don't watch tutorial after tutorial after tutorial. Don't spend 6 months collecting bookmarks on your browser. Build the stupid little applications. Build a cafe. Build a banking system. Build a game. Build your own API. And then break it. Fix it. Break it. Fix it again. And deploy it. This is how you actually become a developer. Okay? So I think we're done here. And our little cafe started out as an idea, and it turned into a distributed application with Java, Spring Boot, relational databases, REST APIs, authentication, authorization, WebSockets, file storage, Docker, PostgreSQL database, Redis, Open API, and all kinds of other things that we just quite frankly didn't have time to cover. But that's okay. So because this little cafe wasn't exactly the point. You were. The whole reason that we built this thing was to give you a path, something that you could follow, something that you could build, something you could break, and something that you can keep expanding as your skills grow. And if you follow this entire series, you should have a much better idea of what your journey looks like. You don't have to know everything. You just need to know what to learn next. So, I guess this is our last coffee together, or at least for this series. But I genuinely hope that you take what we've talked about here and build something interesting. Because there's a point where you have to stop preparing and start doing. You're going to make mistakes. You're going to get frustrated. You're going to write some absolutely terrible code. Trust me, I still do. But every time you build something, you learn. Every time you break something, you learn. And every time you have to figure out why something doesn't work, you're becoming a better developer. So don't be afraid of the journey. Enjoy it. Keep your curiosity open, your skills sharp, and that coffee cup full. And listen, you have my contact information. If you ever need help with along the way, feel free to message me and reach out. Seriously, I would love to hear what you have to build. Thanks for chatting with me all this time.